Okay, good morning, ladies and gentlemen. Today we get to the actually topic of the course, predictive control, after 4 days of intensive background. And as you will see, the predictive control puts together exactly those two areas that you discussed up to now. First 2 days, linear systems, and second 2 days on optimization. So in MPC, we'll combine the systems theory that you learned and the optimization that you learned about last couple of days from Paul Goulart. So we'll have 3 parts to this lecture. The handouts are in the front if you didn't pick them up. And Professor Borelli and I will alternate in terms of the lecturing. When I introduced him, I said a few words, I think, on Monday. He did his PhD here at ETH and then was at Honeywell and is now professor at Berkeley. And at Berkeley, he also leads the Hyundai research lab. Hyundai from the car company, and that's the first laboratory, university laboratory that Hyundai established outside Korea. And he can tell you more about the lab than I can. So I will start, and so this first lecture, part 1, meant as an introduction, so it will be not very mathematical. It will be mostly illustrative in terms of the ideas that are behind and motivating model predictive control, and will also show you some of the applications that have been done of this technique, mostly at ETH and the University of California at Berkeley. So, as I said, first part, main idea, then we'll say why MPC, and I will refer to it from now on MPC, not model predictive control, why MPC is not really replacing what you learned in the earlier classes, for example, Regelsysteme 1 and 2, but it's complementing it. It's addressing a different aspect, and that's sometimes misunderstood. And then in the third section there, I will just give you the mathematical formulation, motivating it, and you will see this formulation over and over again throughout the 3 hours of lectures today. And then we have a number of applications, as I said, most of them either at ETH or at Berkeley. And we'll finish that first lecture with some summary and outlook. What are we going to cover about predictive control today as well as next week? Okay, so what's the main idea? Illustrated here on a racetrack. And if you want, you can think about the real racetrack, or you can think about it as some model car racetrack. What you may have heard about the real racetracks, or I read about in the press, that all those Formula One companies have detailed models of the track, and detailed models meaning not only the radius of the curves, etc., but every little bump in the road is all modeled. So basically, they can run a model of the Formula One race car on the simulation on every Formula One racetrack in the world. And Sauber, for example, would have that, and other car development company as well. And clearly what they also do, they will figure out what is the optimal route to go through the track, what is the optimal speed at each point, etc., to go through that track to reach the best lap time. And so clearly, what are some of the objectives and constraints? Fastest lap time, clearly you don't want to crash. Okay, as indicated here, so you want to avoid the other cars. You don't want to fly off the road. Formula One race cars, contrary to rally cars, you don't want to slip. Okay, you want to stick to the road. Don't want to slip with the back or anything like that. Your acceleration is big, but it's still limited, also because of the traction, etc. So you have a number of constraints. And so the intuitive thing would be you put yourself in the driver's seat, and you know everything, as I said, about the road conditions. You know about curves that come up. You know about what your car can do, etc. And based on this information and those constraints, you are optimizing, finding some optimal trajectory as well as optimal speed at each point that leads you around the track. So you can do that, and that is certainly being done. So you can think about an optimization problem, minimize lap time while number of constraints, don't hit the other cars, stay on the road, etc. And you can solve that optimization problem, and you can actually get a path like it's indicated here that would lead you at best speed, best time throughout that race course. Now the problem is, in the real race course, suddenly things change. There may be a car that moves in front of you, and so you cannot just follow this race course as it's indicated here, because if you follow your trajectory, you're going to hit that other car. Okay, and so the way you have to correct your pre-computed trajectories, you have to introduce feedback. Feedback meaning information about what's really happening, and then use that information to modify your policy that you have worked out ahead of time. And so this would be indicated here. So we have now recomputed, as soon as this red car here realized that the other car is on the road, the originally white trajectory has been recomputed. And we see now again the new dark trajectory that is now taking into account the other cars. So based on the information the car received, what else is on the road, recomputation of the trajectory that is now optimal given the new scenario with those other cars ahead of the red car. And so, in principle, what you will do, you will only apply this strategy that you have figured out for the red car. You will apply it only over some time or some distance. Then you will reassess the situation. Okay, so you will apply what's written here, the first control action. Then you will reassess the situation in front of the car, and will repeat this planning procedure, starting with the new position of this your car and knowledge about what the other cars are doing on the road. So that's the principle that you would go through repeatedly solving an online optimization problem and continuously updating your optimal trajectory going through the course. And so this is now abstracted away from the race course just into a general procedure. So you will start at this time here, you will make a plan like I outlined for you, and then you will implement part of this plan, the first part, so the first few seconds or the first few meters, and then you will reassess the situation, and you will redo the plan again over some horizon into the future. You will again implement only the first few seconds or meters of this plan, and then you will again assess the situation, assess where you are on the racetrack, where the other cars are, and then redo this plan. So this is called the receding horizon, where the horizon recedes further and further into the future. Receding horizon strategy. and you're using feedback. You're using feedback because whenever at this point here you are assessing your position, you're assessing what else happens on the racetrack, and based on this information, this new information, you are replanning. Okay? And this is shown here in terms of our traditional feedback control diagram, meaning you are taking measurement of the plant, and measurements would be now your position, the other car's position, etc. Based on those measurements, you rerun this optimization, as I showed here, given some reference, given some objectives, given some constraints, obviously considering the model of the system, model of your car, etc. You do this optimization, you figure out the optimal future plan, you implement, but you implement only the first one of those actions, or the first series of those actions, and then you do the measurement and you replan. Okay. That's all there is in terms of the basic concept of model predictive control, and you will see that obviously you don't do it only for race cars, you can do it for many other very practical problems that you apply this strategy. But as I mentioned in the introduction, MPC is not a replacement of the traditional control loops that you learned about in the courses that you had up to this point, but it's complementing it. So how are the tasks divided between the traditional control loops and the MPC? The classical design that you learned about, so the design of this controller C here in this classic diagram, has several objectives. One of them indicated by that green arrow here, so there's some disturbance affecting the system. You want to compensate or reject the effect of this disturbance on the output that you're interested in, so that's one objective. The second thing, your measurements are subject to noise. That's indicated here before they are compared to the reference and then the error fed to this controller. So you have this noise effect. Your controller should also be able to reject or at least attenuate or damp this effect of this noise N. You have issues, so those are traditional control objectives, like we addressed them in Regelsysteme 1. You do that by loop shaping. You want the loop to compensate, not to be affected by noise. You want to correct for disturbance effect, etc. That's how you do traditional feedback design. You also want to make the system, the control loop, insensitive to model errors or the changes of model uncertainty, or you can also say you want to make it insensitive to any changes that may take place in the plant itself, some parameter changes. So back to Formula 1, so over the course the tires will wear, so the car will actually change, so the parameter changes, so either you have to update your controller or at least you make your controller here robust, that whatever actions are still will not drive this whole system unstable. So in the changes, stability and performance are preserved as much as possible. So those are some of the objectives that you address with a classic design, and very often you invoke arguments and discussion and analysis in the frequency domain to address that. So frequency domain also means that you are essentially limiting yourself to linear system description. So whatever we do in Regelsysteme 1 and 2, essentially everything is linear control theory. Essentially everything is based on the linear model of the system. That's why you can use frequency domain arguments. If you go to nonlinear, frequency domain really doesn't apply anymore, strictly speaking. Heuristically, people use it, but strictly speaking, it doesn't really apply. On the other hand, when you do MPC, you're doing real-time repeated optimization, as I explained, to choose this control action U. And the dominant issues that you address in this context are control constraints and process constraints. So in general, constraints. Okay, constraints, as I said, constraints on the road, constraints on the acceleration that you can have on the car, constraints on the traction that you have, etc. And this optimization problem allows you to explicitly consider those constraints. As soon as you have constraints, the system actually, the overall system becomes not linear anymore, but becomes not linear. And so in general, this optimization can deal with much more general models than you can do here, certainly with the constraints, but also with nonlinear process models, nonlinear descriptions of the system P itself, in principle. And usually, so here, no frequency domain, essentially everything is done here in the time domain. So this is not replacing this, okay, but this is complementing this, addressing new objectives in a much better way than you can address it in the frequency domain here. Obviously, even before MPC, people have realized there are constraints, okay? That's a very physical, practical requirement, but they have dealt with this in an ad hoc patch manner, while you can address it systematically within the MPC optimization framework. Constraints here details why are constraints important, because every physical system is subject to constraints. And so there are different types of constraints. One is certainly actuators. So you manipulated variables, your motors that change some, drive some flap on an airplane, some valves that you can open and close. They're all subject to motor to maximum voltage that you can apply, some valve that opens some line is completely open, completely closed. There are constraints. In addition, there are constraints, for example, on the rate. How fast can I open the valve? How fast can I move some actuator? So there, from design, from the physical system, there are constraints imposed on the actuators. Then you have constraints that you impose in terms of performance restrictions. Okay, so that's illustrated in this diagram here. So you have a typical response, let's say, from some output responding to some, say, set point change. Now, even looking at this, this does not look good. This has a large overshoot. And you may not want to allow that for a variety of reasons. Quality of the product that you make, or whatever performance parameter you look at, and you may want to limit how much overshoot you have. So that would be a performance constraint that limits the overshoot, and so then after you invoke that limitation, then the response would possibly look something like shown down here. Third type of constraints is there may be safety constraints. Okay, safety constraints, you have some production facility or also some automotive problem. There may be some maximum temperature that's allowed before that temperature affects the physical system, leads to let's say, deterioration of the parts of the system, aging of the parts of the system, etc. So you want some maximum allowed temperature or some maximum allowed pressure. So in practical operation, that's very critical. So there are those safety constraints that basically say, okay, if you go there, you're destroying your system either immediately, then you shouldn't go there at all, or if you go there often, you will over a longer time period destroy your system. So you have those constraints. And the classical control methods, meaning Regelsysteme 1 and 2, those frequency domain methods, they don't really have a capability, a systematic capability to deal with constraints. As I said, it's patchwork, and if you have a multivariable system with many constraints and many inputs, then there's no way of dealing with this in a good systematic manner using the classical methods, they can do it very well within the optimization framework that MPC operates in. And what you do then instead, not to hit the constraints, you just say, I operate far enough away from the constraints, so I'm not going to hit them using classical methods. That's not a good approach, because in general, if the system is well designed, you will usually operate it at the constraint. So, for example, if you build some production facility for whatever, let's say some chemical, for example, then the optimum, it is not equally efficient if you run it at half capacity or full capacity, okay? Usually it's designed for full capacity, so if you run it at half capacity, the efficiency, let's say energy per product produced, money cost, production cost per unit of product produced is poorer than if you run it at full capacity. So you want to run it at the constraints, then you run it optimally. And so if the control doesn't allow you to go close to the constraints, you're losing economically. And again, that you can handle with the predictive control in some optimal manner. So that's the motivation. So let's go to the mathematical formulation. So that's the abstract description of the type of optimization problem that we would solve online. So here, what this means here is we take a measurement at time t, which is x parenthesis t, and we use this as an initial condition, x sub t, for our optimization problem. So we say, okay, this is where we start our optimization going into the future. And from this point, we have a model, here assumed to be a linear model, that allows us, starting from this point, to predict the states into the future, t plus 1, t plus 2, t plus 3, etc., as a function of whatever inputs we may choose in the future. So that's my system model that I use for prediction with future inputs starting from the current state, from the initial state, x sub t. I have constraints, and here I've written this in this abstract manner that every state in the future will be subject to, will have to lie in some part of the state space. So that means that could be an upper bound x, a lower bound x, so x has to lie in some range. And we have written that abstractly, just that it's in some region of the state space, which means just like all the x's are bounded or some more complicated constraints. It could also be that some difference of states, for example, some rate constraint is bounded, and that will lead to a similar constraint like this, not exactly this form. Also, our manipulated variables will be constrained. Those are our u's, again, upper, lower bound, rate constraint, etc. That's indicated by that calligraphic U letter here. So this is our description, and what we want to do, we want to choose our future control action over some finite horizon, number of time steps into the future. So we're looking at our n next control moves from U0 at the present time, at U1 up to UN minus 1. Actually, this should be T, yeah. This should be, so there's a slight error here, this should really be U sub T. So I will write that here. That should be U sub T, and there should be here T plus 1, and there should be at the end T plus N minus 1, okay? Because those are all our future control actions starting at time t. And so I can even take a picture here so we remember this to correct it for next year. Okay. So those are the future inputs that I will calculate in order to minimize some objective functions, so that's our objective function, as I mentioned to you a couple days ago. So this could be, for example, the sum of squares of errors, okay, deviations from the reference in the future over this future horizon n that I want to minimize. And as a result of this minimization, I get the vector u, capital U sub t, so that's this vector that of which I will then apply the first element, and then I will redo, get the new measurement here, get the new initial condition, and redo this optimization. So that's the idea. And so what we're going to discuss today, what we're going to discuss on today is more about how we do this solution. On Monday, you will go into much more detail on doing the numerical optimization. On Tuesday, we'll discuss more about the properties of this problem, etc. But it all revolves essentially around this formulation. There will be a little bit generalization, we'll allow a more general model, etc. But this is the basic idea, is all in here. Okay. Let's just re-represent it here. So again, you have this optimization, you take a measurement, this is the plant state, you feed that as initial condition, you do the optimization, you get this trajectory of future control moves ut, you pick the first one, you implement, that's a little u, small lowercase u here, you apply to the plant, you take another measurement, etc. So that's the idea. Are there any questions to this concept? Okay, if they're not, then I will just show you a number of applications, many of which here that we have been involved in one form or another. So let me give you an illustration. First, from very fast applications, so that means nanosecond range sampling times, to very slow applications, let's say sampling times of weeks. So over that whole range of time scales, you can apply this model predictive control. Obviously, different complexity of the model, different form of the model, different optimization procedure, etc. But the concept is the same. So what do we do in terms of computer control? Let's say you have a multi-core processor, and you want to schedule your processes, and or you want to decide on the frequency at which you run the individual processes, and you want to do that to perform some computation task. And what are your limits? Your limits are, for example, that you have temperature limits in parts of the chip, and those you don't want to exceed. You want to do that energy efficient, so there are a number of objectives. And Colin Jones, who was a postdoc here, is now a professor at EPFL. He worked on this and actually tried it out on a 8-core processor chip together with colleagues at EPFL, applying the model predictive control concepts. So you look at the future, what are the tasks that you have to solve, what are the constraints, how should you schedule your processor frequency in order to meet the constraints, meet the workload, minimize energy. Okay, the power systems. So here we'll talk a little bit more. So here it would be, for example, how to do the angle, the pitch angle of the blades, how to rotate the blades such that you get maximum energy efficiency, but at the same time the least stress on the physical structure of the system. Again, we'll talk a little bit more about this. Traction control was our first application many years ago that we did with Ford, which is now standard even in cheap cars, where you want to make sure that when you accelerate, you don't slip with your wheels. Okay, so you want the maximum traction you get when you accelerate in a way that the wheels do not slip. And so you have a controller that prevents that slipping, this traction controller. And again, we used MPC to do that and tried it out, or Ford tried it out on a car in Michigan, where they went around the hockey ring in order to have a pure ice challenge. Buildings, specifically here is climate control in buildings. I will talk about it more, how to control temperature, humidity, etc., such that optimum comfort, minimum energy. Refineries, you have different, let's say, switching crude oil that you get, one from the North Sea, one from Saudi Arabia. You have to switch between the crude oils. You want to do that in a way that is most cost effective, most energy effective over some horizon of this switching from one crude to the other. Example, very done commonly now in the petrochemical industry. Here there's nurse rostering. Actually, this we haven't been involved in as far as I know. On the other hand, Colin Jones, again, who is at DPFL, was involved in scheduling the assignments of people working at Migros. Okay, so that means each one of those people has limitations when they can work, how long they are allowed to work, how much is the workload, depending on the sales, expected sales. So there's in the evening there's more than in the mid-afternoon, and on weekends there may be more than during the week, etc. And so you can do over this horizon, you can do a constraint of scheduling how the people should work to meet all their constraints and to be there when they are needed in the store. And that actually they had some startup company that provided the software to do this scheduling of workers for Migros. Obviously not only at one store, but at all or many stores. Train scheduling is a type of problem like this, production planning as well. So specifically now, simple illustrations. Ball on plate, that's one of the early applications. So this is an experimental system that's set up in our laboratory. So you have this plate here, and this plate can be turned. It can be turned in the two directions, so you can turn it in the X and then tilt it in the X and Y direction like this. And by tilting it, you can obviously get this ball to move and to go and to describe follow some prescribed trajectory. And the position, originally we had some laser system to determine the position of the ball. Now it is some vision system that determines the position of the ball on the plate. And what you want to do, you prescribe some trajectory, and you want to tilt the plate, obviously with constraints on how much you can tilt it, plus minus 17 degrees, also with a certain rate constraint, how fast you can tilt it. And this ball is described 4 states, basically position and velocity in X, position and velocity in Y. And you have one input in each axis, obviously angle in the X-axis and angle in the Y-axis. And so there were one master thesis he has mentioned. There were a number of semester project theses and so on that were done on the system. And here you see a simple comparison of two controllers. So on one hand, you have this linear quadratic regulator, which you heard about in other classes, which we also introduced on day 2, which I talked about on Tuesday. So this is a simple proportional controller. It doesn't know anything about constraints. So whenever it hits a constraint, then in terms of the actuator, it just stops. Okay, the controller doesn't know about it. It just acts as much as it can, and then it stops. And so you see the result of what happens. There's a comparison between the red trajectory here and the blue trajectory. Okay, so what happens? The traditional controller. So the traditional controller says, okay, I will, for example, I will, it goes in this, it actually goes around. That's important for the understanding. It goes around in this direction. Okay. So what happens, the red system, the ball goes in this direction. Then at this point, the controller realizes, oops, I have to make a corner, okay? But obviously, by the time it realizes, this ball has already continued moving, okay? And so then while it tries to lift the plate, okay, the ball continues moving, and then finally the plate is tilted enough, the ball returns to that trajectory. Here the same happens, this overshoot. And you see exactly this happens in the red and blue curve. So it has this angle at some maximum or minimum position. Then it realizes finally I hit the constraint, and then it changes things, but it's actually too late. And that compares to the blue, which is the MPC, which actually knows from the predictive control before you hit the corner, okay, it knows. It has the predictive capability. Before you hit the corner, I actually have to start tilting my plate so that I don't overshoot. And so you see the blue one, it shifts before, changes, and therefore can follow this square pattern more accurately. So it has this preview capability that improves the performance. And here, okay, I have to make sure now we didn't try this out, but let's see here. Okay, so this is some of the early movies, and you see exactly this following the trajectory. Here also some circular trajectory. Obviously, that's again the replanning, etc. So even if you disturb it, it will return. You can also try it manually, and at this speed it's a little bit difficult to do manually. So let's return here to the slides. Okay. Autonomous quadricopter, those are the little quadricopters that Professor Sigwart has, and we had some master thesis that we did together with people in his group. And so you have those quadricopters, which I'm sure you have seen and heard about. And so you can change the pitch and the speed of rotations of those motors. And again, you want to follow some prescribed trajectory accurately. In this case, it was some application that they want for example, monitoring or doing some repairs. So you shouldn't do in proximity to some other structure. So you don't want to overshoot and run with this helicopter and destroy the equipment on this helicopter while you are running through those trajectories. And so here are some examples. It's now, you see a similar trajectory and a similar performance to what we saw with the ball in 2 dimensions here. Again, you have this 3D movement, and again, you want to track this square, and you see with a simple LQR controller, you get those overshoots just in the same way. And you see it a little bit when you look at the movie. You see, this is kind of, this is a lot more you will see unstable and moving than the next one, which is the MPC. MPC. Okay, now we go to the MPC. So you see a much smoother movement that then also goes into that more accurate tracking that I showed you here at the bottom. Okay, yeah, this is, I think for illustration, it's actually not done here. We'll, yeah, I can, Raft Andrea was probably better or similar things, so I'll skip that. I mean, this is just another helicopter parade. Maybe I shouldn't skip it. It's just to show that we are not only focused on ETH and Berkeley. There are other people doing good things as well. Few, but there are some. Okay, so let's do a little bit of this here. Let's see now. I always have to switch away from this. But you've seen similar things from it. The formation flight is maybe a little bit different. The numbers are bigger. So you can now imagine Amazon delivering their packages in this way. So flying into your living room. Okay, I'll skip the rest. You can also watch it on. You can watch it on the website of the University of Pennsylvania. Professor Vijay Kumar. Let's go back here. Okay. That is now ETH project, our little race cars. So those are cars that we got from a Japanese company. They're at some standard model race car scale. They're very fast, so if you really scale it up, it would correspond to cars going like 400 kilometers an hour, all scaled up. And radio controlled, you can actually use control up to 40 cars on that racetrack. We have some models of those cars, position and the orientation, as well as velocity and angular velocity. Constraints, obviously, on acceleration, steering angle, racetrack boundaries, etc. And again, as I mentioned to you in the introduction, you want to do optimal path planning, path following. And you have to challenge. There are a lot of challenges in the sense what you cannot model very accurately. For example, slip of the car going around the corner. I will show you some of our racing. I must say that some of it has been speeded up, and so some of it is not totally real time. Positioned through an infrared camera and reflectors on the car. All it has been built by students, and I mean not graduate students, but undergraduate students doing their master projects, doing their semester project on various parts, from the visual tracking system, from building this infrared tracking system, to doing the control, etc. And so that's a continuing project in our group. Energy efficient building control. So what's there? I will. Okay, let's take a break. Okay. Okay, I think everybody's back. We'll continue looking at some of those examples. Project that we have been involved in for a number of years. And also Professor Borelli separately at the University of California in Berkeley is building control. And so the objectives there are many. Obviously, comfort issues, meaning temperature, humidity, CO2 level. If there's too high CO2, you will always start yawning Okay, so that's my sensor for the CO2 level or other boredom. So that's a control objective, energy efficiency, light control, etc. Why are we doing it? Because potentially it is possible to save a lot of money, CO2 emissions, energy, etc. And there's some interesting statistic down here where they concentrate only on tons of euros cost per tons of CO2 saved. And you see, for example, that for a number of things that you can change, from lighting changes, air condition, etc., you will actually not only reduce the CO2 emissions, but you will actually also save money doing those various activities that are listed down here. What I was maybe interested in, surprised about seeing, is that if you do replace windows, with better insulating windows, then this will be more money that you can barely make up for through the improved insulation in terms of CO2 reduction for your heating, etc. So windows seem to be clearly, office buildings here in this statistics, not the right investment. What comes here is optimization of building controls. So building controls, you can invest in the building controls and it will save you more money and it will save you CO2 with relatively small changes. And so this is what we focused on. And so here is one idea. You see a trajectory down here. That's the number of days. This is actually, this is 1 week, this blue period. This is 1 week, this 1 week, etc. What you have here is the limits on the temperatures in the room in an office building. So that would be during the office hours here, that's by this blue bar, you have some minimum temperature of 21 degrees. You don't have it during the night and you don't have it during the weekend, okay? The same, you have some upper bound on the temperature. You don't have it during the night and you don't have it during the weekend period here. And so this is an actual followed trajectory. I cannot tell you offhand. I think this was a simulation. That was a simulation where you see that the temperature varied in the room, but it utilized fully the freedom that is offered by the lack of temperature constraints. For example, here on the weekend, in some summer weekend, you exceeded the temperatures far in the room, but it wasn't necessary to do anything because nobody was in the building. Here you drop down below the required temperature on the weekend, and that allows you to save energy. So how do you do that? At least how we did that and how one can do it. You have a model of the building, okay, and you get also predictions about the effects on the building. So for example, weather forecast, we got weather data directly from Meteo Suisse that we would transfer in, I think, hourly rate. We would get data on their local weather prediction, locally meaning as close to the building as we were at, over the next 72 or so hours. That would be updated on an hourly basis, and not only temperature but also solar radiation and other data. Also information about occupancy. Okay, is there somebody there, not there, how many people are there, etc. You can account for electricity price predictions. For example, running your air conditioner at night is cheaper than running it during the day, so you may subcool during the night, so you don't have to do so much cooling during the day. You shift the loads, electricity network loads, all that you can account for in this MPC optimization problem. This is some typical results. and those are again simulations, but we have actually done some implementation on an office building in Basel, an office building of the bio company Actelion. That was in the news because they had some new drug test successful, and those ideas have been implemented and have been running for a couple of years. So here that would be rule-based control. That would be the standard state-of-the-art Siemens rule controller. This is actually the whole year period, 8,760 hours. And here you see the fluctuation. Here, say the upper bound green, the lower bound blue, like I showed before. And so you see this is rule-based. Actually, you're running very much at the top of the allowed range. With this stochastic MPC, we'll talk about the last day, you can operate much better in the range, so you have increased comfort, and it turns out you have decreased energy use as well. Kite power, what's the concept here? Wind turbine, wind speed varies with height. Here you have a profile at 80 meters, so at 800 meters the wind speed would be about 1.5 times 80 meters. Why is that important? Because the power density depends on wind speed to the third power. Okay, so small changes in the wind speed are very important for the ability to extract energy. That's what the wind turbine does. So instead of that wind turbine, where most of the energy you get out of the tips of that wind turbine, because they move the fastest, this actually is there only to hold the tips. It doesn't do much in terms of energy generation. So say you have this enormous structure, but actually you use only the tips. Okay, so the idea is, instead of this, we may as well do away with the structure and just have some kite flying a circle that is similar to what the wind turbine would do. So that's the basic concept that was suggested some decades ago by somebody, but they could never implement it. And now there are research programs to do that. So for example, we are having a program. One question is, should you do the energy generation by, as is indicated here, flying that kite in a pattern 8 here, pulling out that line, and through that pulling, generating, turning a wheel and generating electricity. So you basically generate by pulling out, and then you change the angle of attack of this kite, and then you pull it in with almost no force. Okay, so it pulls, the wind pulls the kite out, you can generate electricity, and then you pull the kite back in, but you change the angle of attack, so it's very simple, very little force to pull the kite back in. So you have this periodic movement, letting it go out, pulling, generating electricity, pulling it back in. Okay, so that's the basic idea. And so here I can show you some video that is done about some of those autonomous kite operation here. So we have this kite, that's collaboration also with EMPA here. And the idea of automatic control is obviously to do all that automatic, to start the kite, to direct the kite in those pattern 8, and to draw it back in. I'm not going to go through the whole length of the movie here. Okay, so that's a retraction phase where it's, as I told you, it's pulled in, change the angle of attack, pulled in, and then it flies out again in this pattern 8, pulls the cable out, and generates electricity. The other concept, which is a concept that's pursued by Makami, which was a company bought by Google, is that they actually have a kite flying, okay, and they have many propellers on the Kite, and those propellers have generators on the Kite, and so you transfer the electricity via conducting cable down to the bottom. Here, the cables are just lines, okay, that hold the Kite. The electricity is generated on the ground. So those are the two basic concepts. Either you generate electricity, so you could say you have little windmills up on the top running, generate electricity, sending it down, or generating electricity by pulling. So those are the two basic concepts. So there are pluses and minuses to those two concepts. I'm not going to go detailed. We'll have it on the web. You can look at it. Okay. Next thing, automotive system. Actually, I will turn over to Francesco Borelli to discuss the Audi. You want to take yours or them? Just continue mine.
So, hello everybody.
Sorry.
Yes, I need this. See this? No. No. Can you hear me? Okay. We don't have a lot of time, and I'll be talking about this during the on Wednesday. So I'll quickly tell you about 3 automotive applications we have applied. We are applying MPC. One is this smart cruise control from Audi. It was a project with Audi. Very simple idea. You're going from A to B, and if there is a traffic jam, there is no need for you to accelerate now. You'll just waste fuel, and you'll get at home at the same time. Right? So if you have a forecast, what you see here, this was an experiment we did in the Bay Area. It started, it was Berkeley to San Jose. If you have a forecast of the mean and maximum speed on the highway, so you probably need to go here, and this guy here, and this. Okay, so you see the line here. Where is it? Okay. Minimum, green is the minimum speed on the highway, and red is the maximum. Okay, and why there is a minimum and maximum? Because you have different lanes, and you can go the left lane or the right lane at the higher speed. So the blue is what the car decides the best trade-off between the speed of the vehicle and the time you get home. Okay, so the idea, you can see you go at 27 miles per hour, then you see that there's a traffic jam ahead, so you go and start slowing down, okay, and then you follow the lowest speed, and then you speed up again here, and then you reach your destination. Okay, so this was tested. You could see that you get at the same time, there was the right trade-off between fuel efficiency and time. I'll talk, the next presentation is about, we have been working a lot with self-driving vehicles on slippery conditions. Okay, and again, you will see this video on Wednesday. The idea is that it's extremely difficult to design a controller that allows to go through obstacles in a slippery road if you don't have a forecast of the road and the conditions of the road. Okay, where the obstacles are and where the friction becomes lower than your current frictions. Okay, and again, I'm going slow. Otherwise, I'm going fast. Show the movie. You want to show the movie? Okay, I'll show you that. I see. So this was one of the several tests. Usually, automotive companies test this type of controls in the north part of the world. So if when I was in Europe, this test here is in North Michigan. There are facilities in Sweden where the car manufacturers bring their cars, test different type of controllers, including this one here. Next, here and here. This is our most recent project with Volvo. Again, the idea is the challenge here is not the slippery condition. The challenge is actually that the human is falling asleep. Okay, and so the forecast, if you have the concept is that if you have cameras inside the vehicle, Okay? You can forecast, looking at your body movement, you can forecast what are you going to do, okay, what's happening inside the car, and using that forecast you can actually avoid exiting a lane. Okay? So this type of controls are called lane keeping. Again, you have to go here. Yes. So the idea is that it's not a self-driving car. Okay, just look at you, look at your hands, okay, and then let the car go. Okay, and if you're going, you can see that if it forecasts that you're going to go outside the lane, it takes over, it brings you inside the lane. Okay, so it's a minimally invasive concept, which is different than a self-driving vehicle. I'll tell you more again on Wednesday about this fine application in the automotive world. This was a graduate student that was trusting a lot the MPC. I wouldn't drive in that car yet. So, yes, okay. This is an old, this goes back to 2008, 5 years ago. The reason why it's in here, because this is probably one of the most complex designs I've ever done. It's about tracking a simple point, okay? And it has to be fast. You want to keep the point inside a given target. Okay, so you have a target area, you want to keep the point in there. But the idea that's called, first of all, there are two eyes that are trying to look at the point, like in a chameleon. And the second concept is that it uses MPC in the form that you've heard from Professor Morari if you see the target. Okay, so this would be a tracking problem. If the target goes outside the square, so you don't see it, what you do, use an open loop. You design a controller to simulate a saccade. So you use an open loop controller still in the MPC framework, but without updating the state. So you forecast where you think the point is going to be, and you go in open loop without updating to your forecasted point. Okay, so you do this saccade, you go, you check in there, and look if the obstacle, the point you're trying to track is in there. If it's in there, you continue with the smooth tracking. If it's not, then you search again in the space. Okay, and this is typical in this type of animals that they switch. We also do that between smooth tracking and saccades. Okay, you see the video, this was done at the Technion. So the idea here, so you see the tracking when it's inside, and then there is a fast, see? So when it goes outside, the only way you don't have, the idea is that you know where the obstacle is only when it's in that square. So when it goes outside, you go in open loop, you know the speed and acceleration of the point, you forecast where it's going to be the next few seconds, and you jump there and to catch it there, to catch the point there, okay? I think we're done with applications. Now the boring part starts, and I'll teach it. So do you want to summarize, and then I'll use my slides? Okay.
So this is just a summary here of where we are and where we want to go. That diagram you saw, that's the plant. We take the measurement of the state, and then we feed it into this optimization problem, starting with the initial condition being the measured state. Compute the sequence of view where we implement one, then resample, re-optimize. Okay. So summary, what you need to have to do that, you need a model. That's a key thing. The whole thing is based on a model, and the quality and the improvements you get depends on the accuracy and fidelity of your model. Then usually you cannot measure all the states. You need to have some observer or filter to get you the states. Then you have to define this optimal control problem, that meaning the objective function that you want to use, the constraints, etc. You need to set up the optimization problem in whatever software you have available, and you have to solve it in real time with the proper speed, etc., that is needed for that real-time application. And finally, you have to do the testing to verify that the whole thing works. So what are the main advantages? As I said, systematic handling of constraints, and that you get when you have a good model, very high performance, high quality performance. What are the challenges? Okay, some of the challenges that we'll address. Number one, implementation. So you have some optimization code that you have to run in real time reliably, meaning it has to come back after your sampling time with a solution that at least, if not optimal, good enough not to mess up the whole system. Okay, and you need to absolutely trust that it's not like no solution found. Okay, try again. Okay, that is not acceptable in this environment. Stability. We haven't talked about it at all. Clearly, we want this feedback loop. We want to guarantee stability with a controller that's not a PI controller, but it's an optimization routine. And with that, we want to do it such that stability is guaranteed. Robustness, when there's model uncertainty. Feasibility, we want to make sure we can satisfy the constraints, not only at present, but also as we move on in time and move on in space with the system. Outlook, part 2, coming now, focusing on what optimization problem do we get, how do we solve it, how do we set it up. That will be continuing on Monday with detailed numerical methods on how to do that. Part 3, also later today, is how to look at feasibility and stability, and then advanced topics later next week on Tuesday and Friday that deal with soft constraints and all kind of implementation issue. Literature, you have our book, which you can download. As I said, you should not print it because it's 500 pages and it changes weekly now. By May, it will not change, is our plan. Okay, and other books that preceded that are also very good. A book by Rawlings and Main, a book by Jan Maciejowski, and optimization books that you heard about yesterday. Okay, I'll get back to Professor Borelli here to start with part 2. Do
you have your part 2 now? Okay. Yes, okay. Berkeley, okay. There's an E missing. So, part 2 is about the solution of finite time constraint optimal control. So in these slides, you will not see the word MPC. So what we are going to do, in the first part, you've heard that MPC is about the repeated solution of finite time constraint optimal control problems. These slides tell you how to solve finite time optimal control problems. Okay, so let's go directly to the main points, the formulation and the issues. Okay, we have, as you have seen in the first lecture, we have a cost function which has a terminal cost, okay, and a stage cost. We call them P and Q. We optimize over a sequence of inputs, U0, UN minus 1. And in the type of norms, we are going to focus on 2 types of norms. A squared Euclidean norm, which gives you the standard, which is the standard one you have seen in LQR, X transpose PXN for terminal cost, X transpose QX, U transpose RU for stage cost. We'll also very briefly touch 1 and infinity norms. So as a cost, rather than using a square Euclidean norm, you could use the infinity norm of weighted sum of the states and of the inputs, as well as an infinity norm or a 1 norm of weighted sum of the states. The constrained finite time optimal control problem, you will see This acronym often CFTOC, Constrained Finite Automotive Control Problem, tries to minimize the costs, J, subject to linear system dynamics, state and input constraints, terminal constraint. Okay? This X, the assumption is that calligraphic X, the calligraphic U, and calligraphic XF are polyhedrons. Okay, so the X belongs in a polyhedron is described by a set of linear inequalities. Okay, this is the problem we would like to solve, and the question is, how do we solve this problem? Okay, first, before telling you how to solve this problem, okay, for the different cases of a square Euclidean norm or one infinity norm, I'm going to tell you, define what the feasible set is. What is the difference with LQR? Anybody? So this is, if I give without constraints, this is your L, and if I use a square Euclidean norm, this is your LQR, linear quadratic regulator. Everybody, finite time LQR. You know the solution to this problem. Now you have constraints, okay? Constraints imply that in general their solution might not exist. So we will define might not exist. We define a feasible set, calligraphic x0, the set of all points x0, all initial states. Sorry. All initial state x0, that when such that there exists an input sequence which is feasible, that when applied to the system dynamics generates states which are feasible. Okay? In general, we define calligraphic xi as the set of feasible states at step I. Okay? So let's try to. I'm going to use. I'll spend 5 minutes on this. It's an important concept. If you want to sketch this, we will have a terminal set which we have called XF. Okay, we have this is at time n. At time 0, we have our constraints. Okay, we call the calligraphic. We call them calligraphic X. Okay, and the question here, we want to compute the set of points which start in X, okay, and can be steered into XF in n steps. So step 1, step 2, step 3, step 3, step n. Okay, so calligraphic x0 is a set. It's a subset of X. Okay, we will use this guy here. Okay, of feasible points. You know that if you start from the states in the red set, there will exist an feasible input sequence that will bring you in n step in XF. Okay, and the state along the trajectory will always be inside the blue box X. Okay, 0, 1, 2, and so on. Okay, so if you take now the generic step I in here, you will have a set which will be a calligraphic xi, and is the set of states for which from which there exists a feasible input sequence. It'll bring you from I to n to the state xf at step n. Questions? So, main difference with LQR, the control is not defined everywhere. The control is feasible. The input exists only in these sets. Calligraphic x0 at step 0, calligraphic x1 at step 1, calligraphic xn minus 1 at step n minus 1. Let's go back to the slides here. Okay. Now, we know where the controller is defined in this sets. How do I compute the controller? Well, simplest case. No state and input constraints and square the Euclidean norm. By the way, in the slides, square Euclidean norm, quadratic cost, two norm are all the same. Okay, and they mean X transpose QX plus U transpose RU. Okay, the no constraints, so it means that the set of states and inputs is Rn plus m. In our notation, n is the number of states and m is the number of inputs. There is no terminal constraint, so the problem is unconstrained. You remember from lecture number 2, your controller is a time-varying state feedback linear controller. That's the solution. Okay, and you know how to compute the gains Fk. You've seen this in lecture 1. Okay? If you let n, now this was for a finite time optimization, if you let n goes to infinity, then you have an infinite time controller, which is a time invariant controller, linear, and the feedback gain F infinity is computed through the equation that you have on the slides. Question is, now I have constraints. Let's remove the assumption that the problem is unconstrained. So what is the solution? How do I compute the solution? Okay? Well, let's do you have slides for both cases, 2 norm and 1 infinity norm. I'll spend some time on the 2 norm. I'll go very quick on the 1 infinity norm. 2 norm. This is, again, repeating the problem just to make sure that we specify exactly what you are trying to solve. Cost function is the sum of a stage cost. Okay, and a terminal cost, X transpose Pxn, and the stage cost. They are square Euclidean norms, and the P, Q, and Q are semi-definite, and are assumed to be positive definite. Standard assumption in the LQR problem. We have a linear system. We have state and input constraints. At each time step, I want the state to be in X. The input has to be in U, and the terminal point have to be in the set XF. Okay? The way to solve this is to use a 3-step procedure and transform the problem into a quadratic program. Okay? And here at this slide tells you the 3 steps. First step is to rewrite the cost, focus on the cost. You rewrite it as a quadratic function of the input sequence U0 and the initial state X0. So you see this is now a quadratic expression in the vector U0, X0. All this transpose, this means this is a row, this is a column vector. Okay? So you have done this in lecture 1 and 2. Basically, it's about matrix multiplication manipulations. How do you compute H, F, and Y? You need to manipulate the system dynamics, A and B, and the original cost, which was P, Q, and R. So H, F, and Y are a function of A, B, P, Q, and R. Okay? So now that we have transformed the cost, compact form, quadratic in the input sequence U0, then you transform the constraints, and you rewrite them as a set of linear constraints in U0 and X0. Okay? So U0 is, again, the vector of inputs. U0, capital U0 is the vector of input of U0, U1, UN minus 1. G is a big matrix. It collects all your state and input constraints. The right-hand side, you have a constant vector, a constant column vector W0, and a constant and a matrix that multiplies the initial state that for a given state becomes another constant vector. Okay? So at the end, you end up with this optimization problem here. And what are the features of this optimization problem? The unknown is U0. Okay? It's quadratic in U0 and X0. The cost is quadratic. Okay? And there's a set it's a constraint problem, a set of linear inequality constraints that involve u0, constant term, and x0. Questions? Do you know how to solve this problem? Yes or no? I hope you do. You have done 2 lectures on optimization. It looks strange because of this x0, right? So, but for a fixed x0, if you know x0 is a vector, the right-hand side becomes a constant vector, okay? And if you know x0, this quadratic term becomes quadratic in u0 and linear in u0. So this becomes a quadratic program, a QP, okay? So that's what the main message of this slide is. You have taken the finite time constraint optimal control problem. You have transformed into the minimization over the input sequence of a quadratic cost subject to linear constraints. The state enters the right-hand side of the constraints, okay, and the cost, it enters linearly, the initial state. For a fixed x0, you use a QP solver to solve this problem. Okay? So this is, you see now, the merging of the word between control and optimization. You need all what they have done, lecture 1 and 2, and you need a solver. You need to know what is a constraint solver, how to solve this through an algorithm, okay, and to get the optimal solution u star 0. Have questions? Let me spend a little bit, a second on this. If you want to minimize, so what is a QP, quadratic program? In case you forgot the past lecture, minimize X transpose QX. That's not a good. Z transpose A Z plus C transpose Z subject to A Z less or equal than B. Okay, this is probably the form that you have seen of a quadratic program. Okay, there are software where you feed H, C, A, and B and tell you what is Z star. Okay. What you have, this is a quadratic problem. What you have here now, we have this optimization problem that for a given x0 becomes a quadratic problem. That's very simple because when you write what you have on the this problem here becomes the mean u transpose 0 h u0 plus 2 times x0 transpose f u0. Sorry, this is, okay, transpose. So you see that for a fixed x0, your linear term, this becomes a row vector, is your C, okay? Similarly, for a when you fix x0, this term here, this is another color, this term here becomes your B. Okay? Questions? Let's go next. So you know, summary, you know how to solve a finite time constraint optimal control problem for square Euclidean norms and linear systems. Well, there was in these steps, okay? If you go back to the 3 steps, step 1 you have done in the lecture. Lecture 1 and 2. Step 3, I went really fast. I say you transform all your constraints into a set of linear inequality constraints, and here, Okay? And that's all what I've said. In the slides, there are details on how to do this, and I'm not going to spend time on it. Okay? What is the basic idea? Well, before, remember the problem you want to solve? It looks like this. It is a polyhedral. The system is linear. Constraints are x is in x, u is in u, and xn is in xf. So these are, and x, u, and xf are polyhedrons. It means they're described by linear inequalities. Linear inequalities, linear systems, gives you a set of linear inequalities. That's the idea. Okay? And so it's about matrix multiplications. Let's do just one case, since you. The case where there are two approaches. One is with substitution, another one without substitution. Rewrite the set of state constraints x as a set of linear inequalities. The set of input constraints, a set of linear inequalities on u, and this is your terminal constraint. Okay? You want to write all these constraints for 0 to n. And so here is your g, e, and w that form your matrix, that form your set of linear inequalities. Okay? For instance, here you can see where are these coming from. Here you could what is the first row? First row is AU U0 less or equal to MBU. This is the first constraint on U0. Okay? This is a constraint on U0. This guy here is a constraint on U1. Okay? What about this row here? This is all zeros minus AX BX. Okay? If you go back, E0 and W are on the same side. Okay? So this row here is the state constraint on x0. So this is AX x0 less or equal to MBX. Okay? What about this one here? This is AX x1 less or equal to MBX. Why? Because you have, that's why it's called with substitution. We substitute x1 with the system dynamics AX0 plus BU0 less or equal to MBX. And that's why you have AX times A here, AX times B here. This is the constraint on U0, and BX here. Okay? I think this is plenty for, you got the message. You can derive, look at the slides and derive the equations. Okay? Yes?
It's important that the constraints are time invariant, or is it just a simple form?
This point is not important. This is done for time invariant constraints, but as you pointed out, AU can be different AUs at each time step. The matrix will change. So you will use AU0, you will use AU1, AU1. Very good point. So this is a more general message than this. The slides and the formulations are for the simplest problem possible. Linear system, polyhedral constraints, and actually not even, you haven't seen a reference here. This is controlling to the origin. There is no reference yet. So the most general form, all what you have seen in the examples are actually have references. They have time varying constraints. They might have nonlinear constraints and so on. Okay? There is, by the way, there is the MPT toolbox you will see in the exercise. Will do this for you. So you don't have to compile this big list of matrices, but it's good to do it once if you really want to understand what is behind the idea. The second, you will, in the slides, you also have another set, the other approach is called the QP with substitution. Very quickly, the idea is not to replace the system dynamics. Okay? So instead of getting a quadratic program that looks like this, okay, so only inequality constraints. In order to do that, what happened to the system dynamics? System dynamics are here, right? Are equality constraints. In order to obtain only inequality constraints, we have replaced them. That's why it's called with substitution. What you can do is actually not replace them, and you consider an unknown vector to be the vector of states, x1, x2, xn, and inputs. Okay? So if you do this, your QP has this form. Why do I call it QP, quadratic program? Because still there is a minimization of a quadratic cost, a vector time quadratic term, vector transpose, subject to linear inequality and equality constraints. The difference now is that your unknown is all the states and inputs, and you have equality constraints which describe the system dynamics. So if you see G0 eq and E0 eq are nothing but x1 equal AX0 plus BU0. x2 equal AX1 plus BU1. Okay? So why we present these two forms? Because they're both very important. We will use the substitution next to show some interesting property. Without substitution is a nice feature. What happens now? You have a much larger set of constraints, because now you see this big matrix of inequality constraints. You have all constraints AX on x0 and x1 explicitly written, but now your matrix is sparse, it's block diagonal. So you will hear on Monday that this class of problems actually, if you use a QP, is easier to solve than instead of having a dense but small matrix. Okay? Sometimes it's better to solve a quadratic problem with a large and sparse matrix of constraints. So time is over here. Very quickly, what is coming next? We will skip. In your slides, there is a star on two-norm state feedback solution. It means that we'll skip it in this lecture. This will be part of the advanced material. You don't have to study for now, okay? And probably not even for the exam. Professor Murray will let you know. So the star means skip it, okay? And the next is actually the 1 and infinity norm. I said I will not spend time, or everything that I showed you for QP, for squared Euclidean norm holds for 1 infinity norm. There is feasible set, x0, x1, xn. What is the main difference? Well, that when you do the conversion, the 3 steps, construction of the LP, you end up with a linear program, not a quadratic program. Okay? So this is the main message you should remember, and I think this is enough for now. If we have time, we'll go back to 1 infinity norm, but at this point, the message for you of the last part of part 2 is that if you use, instead of a squared Euclidean norm, use a different norm, like the 1 and infinity norm. Rather than solving a quadratic program, you need to solve for a given x0, you need to solve a linear program. Okay, and again, because 1 and infinity norm have piecewise linear costs, and Paul has showed you that piecewise linear costs can be transformed into linear programs. Okay? Should we take a break? Okay. Summary of part 2. We're going to part 3. In, what was your one thing you have to remember from part 2? Well, to solve finite time, constrained finite time optimal control problem for linear systems, and square Euclidean norm, quadratic cost, 2 norm. They're all the same. Okay, let me write system and 2 norm. Okay, you need to solve a quadratic program given your initial condition x0. That's the only one. If there is one thing you have to remember is this. Given x0, you need to solve a quadratic program. If you don't know what's a quadratic program, if you don't know what is a quadratic program, go back to Paul Goulard's slides. Okay? Your colleague had a question, what happened? At some point we introduced a feasible set calligraphy x0. What happened to it? Why do we need it? We will need it in part 3. Okay? But already if you go back, if you think about the way we have transformed the problem, okay? This one here, and I ask you, does this problem does it have always a solution for every x0? What is the answer? I change, x0 is initial state. I can measure state and solve this problem, right? Change x0, solve this problem. Can it be infeasible? Yes or no? Yes, can be infeasible. It's a constraint problem. It means that for some states, you are too far. What is interpretation? You are too far from your xf. Your input are constraints. You are not able to reach xf in n steps. Okay? So for some x0, this problem would be infeasible. For which set of states this problem will be feasible? Well, by our definition, in calligraphic x0, this problem will be feasible. Okay? So this is, if you had to sketch calligraphic x0 again, this should be a polyhedron. Sorry. Let's try again. Make it simpler. This is calligraphic x0. If you start, I'm assuming there are two states. That's why I always do this plot in 2 dimension. If I start from here, the QP will be feasible. If I start outside, the QP will be infeasible. Okay? So 2 main messages. Remember the definition of the set calligraphic x0. Remember that to solve a constrained finite time optimal control problem, you need a quadratic programming solver. Anything different from your LQR? What do you need to do in an LQR to compute the optimal solution? Matrix multiplication. F infinity times x. Okay? A matrix that you have pre-computed times x. What do you have to do in MPC? Well, you have to buy a solver. You need to buy a quadratic programmer. You have to design a solver. It depends how much time you have to this complicated iterative algorithm that will give you a solution for a given x0. Okay? So much more complicated. Let's go to part 3. And probably I will not be able to cover all part 3 today. Where is part 3? I think it's this guy here. No, I don't know how to go at beginning. Here, okay. Okay. So message here is to do more math, present a more formal, present the model predictive control concept in a more formal way, and address the issues of feasibility and stability. Okay. Some of the first slides are just repetitions. Okay. Basic idea, you know that Professor Murray spent a lot of time describing the main concept. You would like to solve an infinite horizon problem, okay, where you have system dynamics, you have state and input constraints, and you minimize a cost. And you'd like to solve it very long, so you take into account, you make sure that nothing will happen in the future. Okay, because you have accounted for all possible events that can happen. However, this is very difficult because this problem has an infinite number of variables, and so what we can solve sometimes is a finite time optimal control problem in a repeated fashion. Okay, so it's solved in the same with the idea that Professor Murray showed you: a start at time t with a measured state of the system. I solve this finite time optimal control problem, and I get an input, and I keep. So I get an input sequence, I apply on the first one, and I keep optimizing the next step over a shifted horizon. 2 messages very important for this part of the course, for these slides especially. There are 2 elements that we introduce. We already introduced it in the finite time constraint optimal, in the constraint finite time optimal control problem. The terminal cost and the terminal set. Now you understand there is a simple interpretation here, because the idea of these 2 elements in an MPC framework is try to capture what goes from n to infinity. Okay, so because we would like to solve the infinite time problem, we cannot. because we can solve it only in the unconstrained linear quadratic case. So then if we want to solve a finite time problem, we would like to add a cost so that it captures the cost from n to infinity, and we would like to add a constraint so that it captures the constraints from n to infinity. Okay? So what are again repeated the same slides. Once we know, and now we know how to solve a constrained finite time optimal control problem, especially for linear system and polyidal constraints. This algorithm, a receding horizon control algorithm, a moving horizon control algorithm, model predictive control algorithm, is very simple. Measure the state, solve the finite time problem. You get an input sequence here, okay, the one you see in red. Apply only the first one, trash the rest. The next time step, solve another finite time optimal control problem over a shifted horizon based on new measurement of the state. That's the most important thing. At the t+1, you don't start from what you predicted where the system would be, but you start from x of t+1, which is your measurement of the state at time t+1. And this gives you feedback. So the algorithm is really 5 lines. If you have to write an MPC algorithm, it's very, very simple. Measure the state, obtain the solve the QP. Okay. If this is confusing, this really means if U star is empty. Okay. It means the problem is infeasible. You don't have any. If there is no U star, well then stop. There's not much you can do. The problem is infeasible. Otherwise, you apply only the first element, U star of t, of the input sequence. You discard the rest and repeat the optimization. Okay? Very simple algorithm. Do this all the time. If you play chess, you do this all the time. Okay? A little bit of history. I'll go very quick. You can ask Professor Murari. He knows well, very, very quickly. Around the idea, and this goes back to the 60s. Okay, this you probably were minus 30, something like this. Propoid, he writes a nice paper you can download. It's actually very simple to read. Whereas linear systems, linear cost, and say, I can design a controller by using a linear program. Now, very visionary at that time, 63. Only much later, people start using these concepts. In the 70s, you have the first algorithm IDCOM, okay, 78. Then you go back to, then we go to 79, where dynamic matrix control was quite popular and used in the chemical industry. Okay. Only, sometimes they had strange names like heuristic controllers. And the idea at that time was a controller was a transfer function. Something that was an optimization algorithm with lots of iteration steps was a heuristic. Okay, that was not well understood at that time. Only later in the 83, people connected the operation research world, the QP, the quadratic programs, the linear programs, to the control world. Okay, what's happening today? We had 20 years of studies with just lots of theory on why does it work, when does it work. This is around the 2000. This is period of my research where we looked at MPC for hybrid systems, fast MPC, and I will tell you more about lately on stochastic MPC and MPC for large-scale systems. Let's go to the notation. If you want to read, so first thing before presenting what are the pros and what are the cons, why there is a theory of MPC. First, that when you open a paper, okay, notation can be quite ugly. Okay, and so the idea here is that to present you the main concepts that you can read papers, okay, on MPC. At the same time, you understand why we are using a simplified notation. This is the right way of writing a predictive control problem. Okay, you have a linear system. Again, we are using a linear system models. Okay, but everything that I'm going to say is true also for nonlinear systems. Most of what I'm saying. The parenthesis x of t+1. This denote the evolution of the actual system. X of t+1 is the state of the system state at t+1. This is the input that I apply at time t. Okay? Different from the model that you use in the MPC. Okay, that's why there's it's done on purpose. That's why there is this notation that might look strange, okay, that says that the state that you use to initialize the model in the MPC is equal to the measure state at time t. Okay? Notation given t. Okay, how do you read this, all these elements? Let's look at this input. This is the input from t to t plus n given t. This reads given t. And it's used to specify the fact that the problem is solved at each time step t. Okay? So if you are solving, let's use the next slide, which is actually interesting. It tells you a very simple example of why you need this notation. X of t, we already said, is the state at time t. Okay? xt plus k is the state at time t plus k predicted at time t. So x3 given 1 is the state at time 3 when you predicted time 1. x3 given 2 is the state at time 3 when you predicted time 2. They are the state at the same time but predicted 2 different times. And they are in general different because your predictions change. Okay? So that's what this says, from x3 plus is different from x3 given 2. Even if the time is the same, the prediction is made at 2 different time steps. Okay? And that's why you need this ugly notation. This is xt plus 1 given t will be a function of t plus, st plus k plus 1 given t is a function of xt plus k given t. Okay? Questions? So this is the most general form, and problems should be written in this way. I'll show you in a second that we will make it simpler. Otherwise, it will be a messy slide with all this ugly notation. Before doing that, what is the control action? Control action, remember what MPC does. You measure x of t, you get input sequence, u star of t given t, and then you take only the first element, which is u star of t given t. Okay? So this function f, which take x of t and gives u star of t given t, is actually f of t is the MPC controller. Okay? It's a complicated function. It's an implicit function. Why? Because you don't have an expression. There is an algorithm, a solver, a QP solver that runs and will give you the output. Okay? There is no analytic expression for this function. The closed loop system, if I have a linear system, will be xt plus 1 equal ax of t plus b, and then the controller, which is f of t, x of t. Okay? What is the notation we're going to use is simpler. Okay, and it's the one here, and from now on should be consistently this. If you notice that it's not, then let us know there is a typo in the slide. Okay, notation is much simpler than what you have seen before. What I have done here is to say, let's get rid of this given t. Okay, and let's set t equal to 0. I've done 2 steps. Okay? If you do that, you see instead of having j star of t, I have j star of 0. Instead of having a u star of u of t, I have a u of 0. Okay? So I'm starting everything from time 0, and I forgot about the given t. Okay? I've just removed that from the notation. Okay? Questions? Can I do that? Well, because system, constraints, and cost function are time invariant, that's not a bad idea. The problem, this optimization problem, and your colleague had questions about time varying constraints. Okay, this optimization problem has time invariant constraints and time invariant system and input dynamics. So the only thing that changes at each time step, what does it change? Say x of t. So you're feeding just a new measure state, but the problem is always the same. Okay? For this class of problem, the notation u0, u1, un minus 1, it's simpler and it's easier to explain the issues. Okay? It still is not proper, right? Because don't get confused. when I'm going to say u0 of x of t, it means the 0 stands for the first control action that will be applied at time t. Okay, it's not the time 0. Okay. Questions? So the MPC controller will become used according to this notation, u star of 0 of x of t. Okay. With this notation, then we can go and look a little bit at the MPC, do an examples, and show you what are the pros and cons. Professor Moraes already discussed this a few times. All what we have said applies to linear, nonlinear model. It does. I've mentioned one input, one output, right? Your regular system lines was assume that there is one u and one y. Okay, so this is, I don't care about the number of input and outputs, this works. Time delays, you can put it in there. Constraints, put it in there. Any objective function, minimum time, even if the example that you're seeing are regulating to 0, you can use minimum time objective function, you can use linear function, you can use nonlinear functions, okay? This is why there is a book and why there are lectures about MPC. The cons are actually what you have to focus on, okay? Two main challenges. The first one, speed, okay? It takes a lot for the solver to converge. You cannot upload the solver on your embedded platform. Okay? Lots of research, lots of interesting work. On Monday, you will actually see Domahidi will give you a lecture on how to make solvers which are fast and tailored to MPC. Okay, so this will be Monday. Monday, okay? Today, we'll look at this. Today, and hopefully, I'm not sure we'll be able to complete today. There are issues that are called stability and feasibility issues. Okay, there is a challenge with these constraints. You start, and you're given a state. You measure a state. The problem, the solver doesn't find a solution. What do? You stop the plan, and you stop the helicopter up there. So it's a big issue to have an infeasible problem. Okay, and that's what we're going to discuss today, trying to address stability and feasibility issues. Okay, the example shows how good is MPC, how bad it can get. Okay, a linearized model of an aircraft, 4 states, angle of attack, pitch angle. Angle of attack is the angle between speed and vehicle directions. This one here, speed vector, vehicle direction. The pitch angle is this other one here. Pitch rate and altitude, okay? We have constraints, elevator angle, elevator rate. There is, if this is a rate, this should be a second here. Pitch, this is correct, and on pitch angle, okay? Those are state constraints. And this is an unstable system. Okay, what Colin did is to take this example and say, okay, let's see how I design a simple LQR, I design a simple MPC controller. Let's compare them. And so you see the LQR to the left, the MPC to the right. They both have the same system. Okay, the first noticeable thing is that on the left-hand side you cannot put constraints, right? You just have to tune in so that constraints are satisfied. In MPC, you have constraints. Okay, just say these are my pitch rate, pitch angle constraint, pitch rate constraint, and what was the other constraint was on the elevator angle constraint. The second difference, infinity and -1. This is a short-sighted. This will be an infinite horizon controller. Okay. So few simulations, very simple tuning, not spending much tuning. The LQR is unstable. Okay, you start from an altitude. So the objective here, you start from a deviation of 10 meters from the altitude. So the blue will be 10 here. Okay, this is 10, and you would like to control it to 0. but what happens is that the plant is unstable. Okay? And the way he has designed the controller is to say, this is my LQR, and then I apply, you see the input here? The input here is actually saturated, and there are also rate constraints. Okay, so it's taking the output of the MPC control, the LQR controller, saturating it, chopping it, and applying rate constraints. Okay, that's only a very simple way of enforcing input constraints. It does the same. So again, what you could do now is to spend hours in trying to tune this. Okay, that's one approach. And it would work, that tuning, only for the 10 meters, the simulation that you are trying to do. Okay. The second is to say, okay, let's use MPC, and you can see, well, at the beginning, it only has input constraints. Okay, the elevator angle, and it's not unstable, but it's it's a limit cycle here. Okay, but then what the next step is to have input and input rate constraints. Okay, and you can see that it nicely goes from 10 meters to 0. Okay. Don't know what the. Sorry. So it starts from 10, converts to 0. Okay. The elevator angle is the green one. It goes down, goes up, okay, and then until the plane reaches the altitude. Okay. So what is showing next is actually a good thing of MPC. Okay, how easy it is to have constraints. Yes, another simulation where it starts from 100 meter, and now the input is too high, and the pitch, okay, it seems, it's around 50 degrees, seems to be too high. Okay, so what happens here is, okay, can I limit the pitch angle? LQR, again, this would be very difficult to do it. Okay, it's impossible, not at least at the design stage. MPC, you just put another constraint. Okay, here is your constraint satisfied. Okay. Again, this is a very illustrative example. Okay, first goal was what you have to remember: LQR formulation, MPC formulation. Okay, message is that you can put all constraints and you get stability. Second message is that you can put more constraints on the states, okay, and they are satisfied and will be very impossible to do with standard design technique. Okay. Third message, which is what is coming next, this was my tuning, right? The same LQR tuning and n equal 10. Let's try to reduce n. Why do I want to reduce n? Yeah. Fast. Takes, it's n 10 means how many, let's do the calculations, how many optimization variables? I have two control, what was it? This was one control input, 10 inputs over the horizon. I had 4 states, 40 states over the horizon. Okay, I want to make that shorter. I'll use n equal 4, and here is what happens. N equal 4, you get instability or limit, limit cycle again. Okay, so this issue, trying to understand the link between tuning and stability, is actually critical, is very important. That's what you will see in the next slides. Okay, so the next slides and the discussion is about stability and invariance of MPC. Does it work? Okay, the MPC is a short-sighted strategy, so you have no feasibility guarantee and no stability guarantee. Feasibility means that at some point the problem might not have a solution. Okay? Stability means that even if it has a solution, okay, you will not converge to the origin, asymptotic stability. Okay? Questions regarding this? Why is this happening? Let's look at a very simple example. Okay, 2 states, 1 input, U. Okay, it's a double integrator, and I have input constraints. The input can be only between -5 and 5, and I have state constraints. I want to be between -5 and 5 for both components of the state. And this is my horizon is 3, P and Q are the identity, R is equal 10. Okay? Use this example, and these big matrices are given to you only for as you can. The first thing that you should do is to take this example and write down the QP matrices. Okay? They are here, so do it as an exercise in MATLAB so you got the message and compare them with H, F, Y, G, E, W that are on this slide. Okay, that's the only reason why they are provided. I'm not gonna spend time on it. Here is what happens when we apply MPC for two different initial states. The black one, that I'm circling with blue, and the red one. So the black one starts at the point circled with blue, okay, and it converges. It converges to the origin. That's where we want to go. Okay. What's happened to the red one? The red one starts feasible. There was a feasible solution. Okay. You apply the first control input. You end up here. The problem is feasible again. You apply the first input. You end up here. At this point here, this becomes infeasible. For this initial state, there is no input sequence that keeps you within the -5, 5. There should be a 5 here, 5 here. Okay? And the control input is between -0.5 and 0.5. From this point, the problem is infeasible. You understand the issue here? Yes?
So that means there must have been noise, right?
No. That's very good. You have a very good point, but that's what is interesting about this idea, about this, the challenge with this, that this is perfect model, no model mismatch. What I'm using in my prediction is exactly what I am using in MPC.
So there was not enough time steps into the future.
Exactly. So I'm short-sighted. Okay? At Berkeley, usually what I say, this happens to me when I want to go home. I'm very stressed, and I start. So my goal in my brain is to reach home, right? Go there, and then what I think is I have to get into the car. Then I think which path I have to take, and I keep optimizing and see maybe I'll change the route and so on. Then I get close to home, park the car, say, damn it, the home keys are in the drawer. So I started infeasible, right? But I didn't know because I was short-sighted. The keys were not in my pocket. Okay, because I was short-sighted, it looked to me that I was feasible. I could reach home, okay? But actually, because I was short-sighted, I didn't forecast. If I had pictured the door, I would have known I was infeasible. I had to have the key in my pocket, okay? So this is what's happening here. The guys goes at speed. Okay, I can do it in 2 steps. There is a momentum here. This is an integrator. I can do it. Oh, and now from here, I have too much inertia. I cannot bring the system back. I will go outside the boundaries, okay? So that's the challenge, even if there is no model mismatch. So the horizon has to be long, okay? And or there are other techniques, and that's what I'm going to discuss. So what I've done here, this simple plot tells you the circles are the initial state which are from which the problem is infeasible or will become infeasible. Okay? And the squares are all the initial states from which the problem will be always feasible. Okay? So this, let me try to code this set here. It's actually a very important set. That's what you would like always to have. This is the set of all states for which if you start in there, you will be feasible at step 0, 1, 2, 3 until infinity. This is called a maximum invariant set. It's called O infinity. We will not spend much time, but there are more slides about the description of this set next. Okay? What you want to avoid are points like this, all the points outside, because from this point you start feasible and you end up infeasible later in the future. Okay? So the other challenge, we talked about, this closes the feasibility aspects. Okay? The other challenge, okay, can I play with tuning and somehow solve this issue? Okay? The answer will be from this example is that very complicated. Okay? So it's very difficult to play with tuning and get an always feasible controller. Okay? Same, is it? No, actually it's not same. This is an unstable system, 2 states, 1 input. 2 states, you will always see examples in 2 states because they're easy to plot. Okay? Input constraints, state constraints, both components between -10 and 10. Here's what happens. In these examples, what we are doing is decreasing R, okay, and increasing N. Okay? So R, the first, we have R is your tuning knob on the input. Okay? Decreasing R means that you are detuning the control. You're using less input. Okay? And N, you're making the horizon longer. So let's see what happens here. So first step, lots of R, okay, short-sighted. All the points are basically will become infeasible. There is no point that will converge to the origin, which is this here. Okay? So notice the green area. Let me use this color green. This is your calligraphic X0. This is the set of points, initial state of which the problem was feasible at time 0. Okay? So you start from point inside the green area, you find a solution time 0. At time 1, depending on the point, you might not find it. At time 2, all the points will become infeasible later at some later time. Okay? So remember that your calligraphic X, so your original state constraints, so making sure that you have a good grasp on these sets, okay? Calligraphic X.
I think it's just the calligraphic X, the green thing. No? Because it's not what will, X0 is what will remain feasible.
No, X0 is what is feasible finite time. So calligraphic X is the blue one. Oh, I did it green again. I
think the green thing is where the U's are allowed.
At times, exactly. Yes, we call that calligraphic. We call that calligraphic X0. Okay, and calligraphic X, which was, our state, the box where I want to keep my system in, was -10, 10, right? This was my calligraphic X. Some points here, if you start from this point, this problem is not feasible at time 0. Okay? If you start in the green, you're feasible at time 0, but you'll become infeasible because of the tuning and everything else at later times. Okay? Questions? Step tuning 2. I'm detuning the controller and I'm increasing the horizon. What's happening? This is tuning 2. What is the observation? Some points now start becoming stable. Okay, you go from, I believe those are not the dots but the stars. Okay, if the star goes in here, this star goes here. Those dots will still be, from the dots you will go out. Okay. So in X0, which is the set of feasible states at time 0, some will converge to the origin, and some will go out. Okay? And you see what happened to calligraphic X0 became smaller. Anybody wants to guess why that's happening? Okay, this is more. Yes.
Well, because our horizon is longer, we already know that we are going to reach an unfeasible point.
Perfect. Okay, and as I get longer horizon, okay. You get this Professor Murari tool. Now he's not here. I can complain about this thing. So what is this? Okay, so far was going okay. Let's try again. 1, 2, 3, 4, and 5. This is my x0, okay? And again, smaller. But what happens here is that more points become converge to the origin. Final message of this slide, just I don't want to make it too long. It's complicated. If you start playing with Q, R, N, you go nowhere. Okay? But you need to remember to look at the plot to the right. Okay? You need to remember 3 sets. Okay? There is the big one, minus 5, 5. Okay? I think we always sketch it with blue. Okay? Which is the set where you would like to keep your state in, blue. Okay? Then there is the set where the problem is feasible at time 0, which is the one I'm going to, in this slide is black. Let's use black. Okay. Okay, in black, inside the black one, this is the set of initial conditions that make the problem feasible at time 0. Okay, this we called it. What did we call this? There's only one thing you have to remember: calligraphic x0, right? Okay, and then inside this set, there are the points from which, if you start feasible, you will always be feasible. This is the green one. Okay. We call that O infinity. Okay. So what would be a good design? What do you think we'd like to get? Yes? Yeah. So if something is not feasible, I want to know when I turn on my helicopter, my dishwasher, my car. I don't want to discover it later. Okay. So the first goal is O infinity equal to x0. Okay. And the second goal, I'd like to get goal 2. What if I do that and x0 is 1, very, very small? Not good, right? Goal 2 is actually to have a large x0. Okay? Because I could provide the first one be true, but then it's only true at the origin. It's a useless controller. Okay? So the rest of the slide shows how to do that. Okay? What time is it? Do we have some time? Yes, some time. Okay. 3 minutes? There are the 30 slides. Okay, so let's summarize, then we'll see. We'll continue on Tuesday. Summary: finite horizon is what you like to get. With constraints, hopeless. Excuse me, the infinite horizon. Receding horizon control is the thing that you can do. Okay, but 2 issues: feasibility, you might become infeasible; stability, even if you are feasible, you wander around and you don't converge. Okay, how we are going to address this? Here is the trick: terminal cost, terminal constraints. I'll show you that by playing just with these 2 things, terminal cost and terminal constraints, you can guarantee feasibility and stability. You don't have to play with horizon, Q, N, terminal costs and terminal constraints. Okay? And The idea is that, well, what is the idea? Is that because the infinite horizon all of these nice properties, if I can find a terminal cost and terminal constraint that mimic the infinite horizon, then I will also inherit the nice properties. Okay? And quickly, I restart from here on, I believe, on Tuesday. But so if you want to play with MPC and have it stable, the first thing that you do, very simple trick, terminal constraint equal to 0. Xn equals, so your xf, the set at the end is the origin. If you set this, if you use this, then it is going to be always feasible and for all feasible initial states and stable. And be careful, everybody say, oh, this is trivial. It's not trivial. You have, don't remember, you're solving in a finite, in a moving horizon. So your 0 moves. 0 to n, 0 is here. 1, now that 0 is n plus 1. 2 is here, right? So your terminal constraint moves. Despite this fact, this will guarantee stability, okay? And persistent feasibility. This was a proof, this was from Gilbert. It goes back to 40 years ago from Michigan, and basically everybody else then has followed this proof and extended it. The second thing that you will learn, this is not desirable. Why is it not desirable? Or what is wrong with this terminal set equal to 0? Yes? Yeah, because you need a long horizon. Imagine an MPC with 2 steps. It means that in 2 steps you want to reach, you have to be able to reach the origin. Okay, so you need a very long horizon, or you will have a very small feasible set. So goal 2 is not satisfying, right? So this is why nobody uses this, but then you have to enlarge the feasible set, and I'll show you how to do that on Tuesday. Okay? So on Tuesday we'll continue from feasibility and stability of MPC, the proof, and we'll be done with, this will conclude the main part of MPC. And then it will be extra material on Wednesday, maybe, no, on Friday maybe.